Okay, so we start. So the today's topics. So first, I will do chapter 7. So chapter 7 is the moving beyond the linearity. So if the variable between y and x, relationship between variable x and the variable y is complicated, what should we do? So that is the thing to discuss. And after that, we discuss the final presentation schedule. Then if we have time, then I will quickly go over the later chapters, chapter 8 to chapter 10, because to plan the final presentation, maybe you need to know what will be covered in the rest of the class. Okay, so chapter 7 slide. Sorry, I have uploaded slides just before the lecture. So if you have not downloaded it, you can download it. You can download at any time. Okay, so chapter 7, the moving beyond linearity. So statistical model often assumes the y and x has linear relationship. What's the reason? Because it's easiest way to model it. So whether or not it's the truth or not, then often we use the model the y is equal to beta naught plus beta 1 x. And this is a statistical model. So we have additional term plus epsilon. So in mathematics, we have maybe two equations for two parameters, and we can solve for it by the linear equations. Then statistical model, that we have more observations than the number of parameters. So we cannot perfectly determine beta naught and beta 1, but we will allow error, the epsilon, and we want to minimize the sum of squared errors usually. And if this is not appropriate, if the pattern between y and x is not linear, then what should we do? So we study several ways in chapter 7. And the first one, we have already studied it. So that is the the polynomial regression. So beta naught plus beta 1x plus beta 2x squared, and so on. So is this model linear in statistical sense?
Yes.
Yeah. What's the reason? Okay, yeah, so it's linear. The answer is correct. Okay, so answer is correct, and it's linear because it's linear with respect to the beta naught to beta d. So this is a linear function of beta naught to beta d. And in statistics, the main topic is how to estimate the model, how to estimate the parameters. So as long as the model is linear in terms of beta naught to beta d, then basically the theory is the same as usual linear model. So this is linear model. So when statisticians say linear model, that means the linear with respect to parameters. So this is linear model. And yeah. And next, we consider the logistic regression. So logistic regression is what? The logistic regression, the y is binary, and the probability of y is equal to 1 is considered. So probability is a kind of expectation. So if we take expectation on both sides, the epsilon disappears. So basically, we don't have an error term in logistic regression model. So logistic regression model, that we have beta naught plus beta 1x originally. Yeah, and since the probability is between 0 and 1, we have some link function. So we have logistic logistic function here. So we have maybe f of this. So f of t is equal to e to the power t over 1 plus e to the power t. Always I was confused. This is inverse logistic function or logistic function. So yeah, actually this is the logistic function, and the inverse of this is inverse logistic. So we can say f inverse of p of y is equal to 1 is equal to beta naught plus beta 1x. Then f inverse is inverse logistic function. So one characteristic is we don't have an error term, but that is because we have already taken expectation. Probability is a special case of expectation. Then this model can be modified by adding more terms, such as beta 2x square plus up to beta d xd. So this is just the this can be estimated in the same way as the usual logistic regression. Yeah. So yeah, so this is similar to usual, the logistic regression. Or yeah, you can also think about in this way. We have x and x square and x cube up to x to the power d. So x itself, we can say that is x1, and x square as x2, x to the this power as x sub d. Then just this is a multiple linear regression model with d variables. And logistic regression, the same thing applies. Yeah, so this is the an example that the polynomial regression is applied for data for age versus wage. So this is the sample unit is individual, and this survey they studied the age and the wage of individuals, and you can see that around maybe age 30, maybe 30 something to maybe 60. Some people have higher wage even around here. And the 20 to maybe 30 to 35, most people have lower wage, and the wage is increasing over time. And after 60 years old, or maybe 63 or 65 years old, okay, so actually the less observation, but the maybe wage goes down. That's the probably this is the US data. And this pattern does not look linear. So age increases, it has this arch-shaped fitted line we should have. So probably it's good to at least add quadratic term, in addition to linear term. And actually, this fits the fourth degree polynomial to capture a little more complicated pattern. We have some plateau here, so maybe the quadratic curve isn't enough to describe this. And this is linear regression, and this is logistic regression. And the logistic regression, X is the same, predictor is age, and the response variable is the probability that wage is more than 250, probably $250,000. And the estimated, okay, so these are the plot. Okay, so some, the small number of people get the more than $250,000. You can see here. And the people between age maybe 30, maybe 33 to maybe age 63 or something. So they have higher probability to get higher wage. So you can see the probability is higher, and probability is lower for age up to maybe 33 and after maybe 65. And the solid line is the fitted line, and the dashed lines are some prediction interval. And basically we have less observations around here, and also it's the near the end of the data set, the predictor values, so it's harder to make a prediction. So range is wider. You can see the prediction interval is wider. Oh, I think that this is probably the confidence interval because the coverage is so small. So confidence interval for the curve. And the logistic regression, we have complicated function f. So probably just the easier way to see is this band, the center to the upper bound gets larger and larger as age increases, because we only have fewer observations. And it gets wider and wider. So basically the image is that this one also gets wider, but we have the logistic function f. So if the value is close to 0, then anyway, so it's really close to 0. Everything is really close to 0. So probably this, the purple solid line means maybe 0.01, well, just 1%, but this one probably, the lower bound is 0.00001 or something like that, but almost it looks the same. So that's why it looks a little strange, but the fact is that if age is higher, it's harder to, the estimate confidence interval. Confidence interval gets wider. Yeah, so in both cases, the polynomial regression is useful. And that has already been done in the past. And do you have any questions? Yeah, so in our language, the one way to fit this is the y on x and the I of x square. This is a little strange code, plus I of x cube and so on. So that is one way. And the other way is the y on polynomial of x and maybe 3 in this case. And if we use this one, we choose slightly different basis. So we use still the same terms, the linear term and quadratic term and cubic term, but those terms are adjusted, not just x and x squared and x cubed. Maybe it is x minus 1 and x squared plus x and x cubed minus 3x squared plus x or something like that, so that these variables are not correlated to each other on the data set. So polynomial regression, so these are not correlated. Coefficients are adjusted so that these variables are not correlated, so we don't have multi-collinearity. So basically, it's a better way to fit the data. Okay, so section 7.2, step functions. This is totally different way to fit the complicated curve. And this is by step functions. So maybe this is an easier way to go. So we just assume that the wage is constant on some specific interval. So then we estimate this for each interval. I think this one probably we have 4 intervals, 1, 2, maybe I write here 1, 2, 3, 4. So at first we have to set the threshold, maybe threshold 1 and a threshold 2 and a threshold 3. This looks just that we made the interval into 4 equal intervals. Possibly that we can set 4 intervals based on the number of observations in each interval. So for each interval, we estimate the level. Then we can get at least the more complicated pattern than straight line. At least we see that the wage is lower on lower age and higher age, and in the middle it's higher. And logistic regression, we can do the same thing. Yep. And what should we do? So basically, this is a little bit more difficult to fit. So at first, we give not points. In this case, the 4 intervals. So k is equal to 3. So we have to pre-specify the C1, C2, and the C3. And in general, C1 to CK. Then after that, we fit this model. So yeah, so in this case, just we divide the entire interval, entire range, entire domain into 4 intervals. So we can specify the 3 not points, but that should be the pre-specified. Then after that, this is a linear model. So is it a linear model or not in total? Maybe answer isn't as clear as the previous question. Once you decided not points, it's a linear model. But if you can decide not points, or you can decide the number k, that choice cannot be done simply. So we need some more complicated things. And generally, this is hard to optimize these numbers. Linear model estimation is just minimizing some quadratic function. So it's easy, but choosing the threshold and choosing the number of not points, that isn't really easy. We have to rely on the more computational methods such as cross-validation. Yeah, so certainly it makes sense. And at least it has some positive size. For example, if you fit the quartic curve, the 4th degree polynomial, maybe the curve is like this, but if it extrapolates, then it's very unrealistic value can be observed. For example, at age 100, the weight should be negative, or age at 5, then the weight may be negative or something like that. So, but the step function is, at least robust against the, extrapolation. So if age 90, maybe we can just assume that's the same as age 80. So that's probably better than just we extend the quartic function. Do you have questions?
So these Ks, they're not necessarily evenly spaced.
Yeah, it can be.
Okay.
It can be non-evenly spaced. That's true. Yeah.
Okay. All right. That's it.
Yeah, it's a little ad hoc, but yeah, certainly you can do that. Yeah. Yeah, maybe the one complication is that if you handpicked the C1 to CK, then basically you have some degrees of freedom, right? So even if you have only 4 pieces of variable, effectively you used more parameters, right? Maybe you use 3 more parameters. And that is hard to compare. For example, you fit the cubic curve and the step function with 4 levels, then it looks that we have the same levels. But if you also consider, handpicked the not points, then basically you have more freedoms. So probably you have to do cross-validation if that your model is better than other models. Okay, so that's a good question. And any other questions? Okay, so the next one is the basis functions. So the first polynomial regression, so we use x squared, and x cubed. And the next step function, so just basically the indicator function for each of the 4 intervals that we defined. If we generalize the idea, okay, so we can define any function of x, b1, b2, b3, any function, maybe some step functions, or maybe sine curve, or yeah, maybe sine curve with higher frequency or a polynomial, any curve you can define. So in general, if we have these basis functions, B1 to Bk, then you can fit this model. So basis functions should be given in advance. For example, if we fit the temperature data, maybe this is the day, and maybe 10 years of temperature, 0 to 3,650. And maybe this is too large, so maybe 5 years of data. So 1825. Then the temperature looks like this. Then maybe you decide to fit the sine of fit this on the sine of maybe, okay, so the period is 365. So sine of the 2 pi t divided by 365. Then this has the period of 365. Then maybe you decide also you take the cosine of 2 pi t over 365. But maybe this pattern is more complicated. So you decide to use the period of 182.5. So this function has the period of just a half a year, and also cosine of this or something like that. So then you can define the B1 to B4 as these variables, these functions. Then you can fit the y on intercept and these 4 variables. That looks more reasonable than just fitting the quadratic function or just 4-step functions. So step functions doesn't make sense. So suppose we have 4 pieces, then we have 5 years. So first 1 year and 3 months, we assume some level, and the next 1 year and 3 months, we assume another level. It doesn't make any sense, right? So the basis functions really depends on the context. So you can optimize, you can choose the functions which are suitable for the data. And once you define the basis functions, then this model is linear. So you can estimate beta naught to beta k easily. So the choice of basis function is difficult, maybe.
Are you only using one predictor? It says
yes,
xi
so
for
yes,
all of them.
that's true. So
Okay.
in this chapter, we are considering the relationship between y and x. So, but the relationship is complicated. We don't have other variables. Yeah, and of course, if you have multiple variables, then you can set basis function for each variable. So that is possible. So if we have another variable z, then we can put maybe gamma 1 times maybe the c1 times zi, and maybe gamma 2 times the c2 times z2 zi, and so on. So it's possible. But here, basically, we focus on the relationship between y and x. And I think in maybe the last section, last 1 or 2 sections, we consider multiple variables. Yeah. Yeah, so another example is as polynomial function. So B1 to Bk, that we choose the orthogonal basis. So another benefit of using this kind of sine curve, cosine curve is usually these are orthogonal. So if you have studied Fourier series, then you can see that it's easily you can easily find the orthogonal 2 waves. Yeah, so that's the section 7.3. So yeah, already you have studied several techniques to improve the fit of the model. Yeah, any other questions? The basis, yeah, orthogonal basis and the sine curve, cosine curve, those are usually common applications of basis functions. And except for that, yeah, so next one, the splines. This is based on the basis functions. So next one is regression splines. Have you heard of splines? No. Anyone have heard of or have used the splines? No. Okay, so splines. So we use basically polynomial of certain degree, but we also allow not points. So that means we assume cubic function for the relationship between y and x, but we have the two curves. X is less than c and x is larger than c. Yeah, so sometimes we have some change, right? So for some disease, if some innovative drug has been invented, after that the number of cases dramatically decreased. So we have some event at time c, then it's reasonable to separate it into two cases. So of course we need more parameters. So if we fit the cubic curve for each of the period, each of the interval, then we need twice as much parameters. So we have 8 parameters here. And of course, we have to decide C also, but for now, we think about the case that C is given. Yeah, but usually we don't want to fit this kind of model without any restrictions. So suppose that we consider maybe temperature trend from maybe 1,500 year 1,500 to today. Then maybe we have some break point in 1800 industrial revolution, but at least we need some continuity. So suppose this is 1,500 and okay, so 1800 and the 2000 and so on. And okay, so temperature, maybe annual average temperature is, okay, so maybe like this, and then after that, then maybe we have some rise in temperature. Then, okay, so suppose that this is the break point, then we fit the data, but we don't want to fit, for example, this line and this line, because the temperature does not jump at the 1,800 years. So it's maybe this is not good, but maybe at least we have to fit in some way. So like this. So we don't want to have this because physically the temperature cannot jump at 1,800. So at least we need continuity. We need some restriction that this point and this point should be the same. Or some physical problems, even this curve should be smooth at the 1,800 or something like that. So we need some additional assumptions for this. Yeah, so that is the idea of regression spline. Yeah, when I worked for a bank, then in the first year, I was asked to do some analysis, and I'm not sure what's the data, maybe unemployment rate or consumer price, and like this data we have, and my boss asked me to fit the linear, the straight line for each time period, and find the best, change point. But at that time, we didn't impose any restrictions, so it sounds pretty unnatural. So we fit straight line here and a straight line here, so it's not continuous. So, but usually when you fit the model, we want it to be continuous. Okay, so spline is a sophisticated way to do that. And okay, so regression spline is basically we have the basis functions. So basis functions, yeah, so basis function is basically prepared for each interval of time period. So suppose we have 3 time periods, then C1 and C2, and we need one regression, the one basis function for the period 1. Then in addition to this function, so maybe, okay, so the base is like this. If this is cubic function, the base is like this, right? Then we need the additional one. So this is, okay, so B1 or something. And we need additional function B2. So additional function makes the fitted curve as, for example, this. So the difference between this and this is B2. To be exact, maybe B2 times B2, beta 2 times beta. So this may be beta 1, beta not is always there, but this difference is beta to B2. And after C2, we fit another curve. So maybe, so this difference is basically the B3, beta 3, B3. So in this way, we can prepare one basis function for one interval, one additional interval, then we can fit a good model. And we, so the cubic spline assumes that for each one, so B1, B2, B3, so these are cubic that we assume. And also that we have, okay, so K knots. So here are the 2 knots. So K is given number. So we prepare the given number. And also that we assume that the entire function, entire curve is continuous and the same first derivative and same second derivative at knot points. So we cannot discontinuous at C1, C2, and at C1, it should be smooth. And even we differentiate this function once, still it should be smooth. So that is the requirement for cubic function. So basically that we connect the cubic curve very naturally to make the overall pattern. That is the cubic spline. Yeah, so why? Yeah. And how to construct this? So at first, okay, so suppose that we have 3 periods, then we need the function for this first period. And the first period, we have intercept, linear term, quadratic term, and cubic term. So we have 4 parameters we need. So basically, in addition to intercept, we need x and x squared and x cubed. And after that, okay, so what is B2? What is the basis function B2? Okay, so we continue this trend. I think it's not linear, so maybe we need some curvature. So yeah. So after the passing this C1, that we need another function that is x minus C1 to the cube, x1 minus C1 cube. So that function is needed. So to be specific, the B2 should be x minus C1 cube if x is larger than C1, here C, and if less than that, the 0. Because basically we explain the trend change after C1. So until C1, basically this function is not activated, so it's 0. And after that, the x minus the C1 cube. X minus C1 cube only, changes slightly when x is around c. So we can smoothly, change the trend from at C1. Okay. Until C1, we only have beta naught plus beta 1 B1, and after that, we introduce another cubic curve, but that starts at 0 and slightly changes. So in this way, that we can make that the curve, the continuous and the first and the second derivative exist. So it's smooth, very smooth. And we need this curve at each knot point. So if we have 2 knot points, then we have another one, x minus c2 cube. And we have k knot points, then x minus c sub k cube. So in this way, we can fit the regression, the cubic spline. Yeah. These are some curves. So if you just fit the cubic curve for 2 time period, it looks like this. So it looks strange. It's not continuous, and and the continuous, the cubic, piecewise cubic. So if we restrict the case, that restrict the function so that the value is the same at the knot point, then we have this cubic curve and this cubic curve, but still it doesn't look natural because we don't have a smooth point here. And the cubic spline is here, so it's very smooth, so it looks natural. Maybe you don't feel it's not as natural as one cubic curve, but at least it's very smooth at here. So this is the lower degree one, so the linear spline. So we assume that this is the beta naught plus beta 1x, and here beta, this may not be, yeah, that's fine. And this one is the beta naught plus beta 1x plus beta 2 times b2x, and the b2x is equal to x minus 50 if x is larger than 50, and 0 if x is less than or equal to 50. So in this way, we can smoothly change the trend. So this is linear spline, so the just first degree version of the spline. Yeah, so in this way, we can define cubic spline, and this has the another benefit. So it's smooth, that is one benefit, but also we can save the number of freedom, the degrees of freedom, the number of degrees of freedom. So in this, the piecewise cubic function, basically we have how many parameters in this to fit this model? For each period, we fit cubic curve. Maybe some bonus credits for the correct answer. So how many parameters? How many coefficients, including intercept?
7.
7. I think it's 8, right? 4.4 plus 8. 4. So yeah, 8. Yeah. So how about maybe a more difficult one? This one, continuous piecewise cubic. So that means that both are cubic, but we have restriction that this is continuous at age 50. Anyone?
Would it be 7?
Yeah, you're right. So who said 7?
Sai.
Sai, okay. I will give 2 points for Sai. So we have, four parameters, and we have 4 parameters, but we have one restriction, so we have to, subtract 1. Yep. So this may be bonus credits. So cubic spline, how many? parameters? Anyone?
Also
Is that
7.
one also 7?
7.
No. So cubic spline, they should be continuous, and also the first derivative and the second derivative should coincide on the left and right side.
Is it 5 or 6?
Yeah, you're right.
Yeah.
So Antarang. Yeah, 5, because we have 4 parameters here and we have 4 parameters here, but we have 3 restrictions. At first, the value out here the coincide, and also the first derivative out here, the coincide on the left-hand side and right-hand side, and the second derivative coincide, so 1. Or even without thinking that, you can see the previous figures. So originally, we fit the y is equal to beta naught plus beta 1x plus beta 2x squared plus beta 3x cubed, right? Then after that, after the change point, that we add this one. So h of xc, in our case, maybe x50. Then we have another one, beta 4. So this is the entire regression model if we have only the 2 pieces, 1 knot point. And you have 1, 2, 3, 4, 5 parameters. So we can save parameters. So if we fit the piecewise cubic regression, that we have 8 parameters, but here we have only 5 parameters. So we can save the number of degrees of freedom in a good way. Yeah, of course, the linear spline, that we have much less parameters, because originally we only have 2 parameters here, and we only have 1 additional parameter, so 3. So this is the degrees of freedom, df. Yeah, so suppose that we have 3 knot points. I'm not sure if we have this kind of question in a quiz, probably there is. If 3 knot points, then how many parameters for cubic spline? If we have C1, C2, C3, how many parameters in total? Like this.
Is it 6?
No. We have 4 parameters here. 1 additional, 1 additional, 1 additional, so 7. Yeah, in the previous page that we have, okay, so at first 4 parameters, then after the first knot point, we have beta 4 times, this one. So x minus C1 cube plus, this is the beta 2, and the beta 5, so B2, and this is another basis function, and this is another one. Then epsilon, so we have 7. 4 plus 1, 2, 3, so 7. Excluding intercept, we have 6. But so theoretically, we can think about 5th degree spline with maybe up to 4th derivative coincide on both sides. So that's the way to go. And yeah, do you have any other questions? Or if it's not clear how many parameters are there, you can ask me so that maybe I can create another question. Yeah. So the cubic spline that doesn't have too many parameters. So if we have just piecewise cubic function and 3 knot points, then we have 4 plus 4 plus 4 plus 4. So we have 16 parameters, but the cubic spline only 4, 1, 1, 1, so it's only 7 parameters. And the next one is the smoothing splines. So this is a good one because often it's really hard to decide knot points. So hopefully we don't want to decide knot points because we are not sure how to optimize it, how to choose the best knot points. Also, the number of knot points are not clear. So the smoothing splines, they solve that question. And basically, we don't really have to worry about the knot points. The idea is that so we prepare as much knot point as possible. So if we have ties, maybe we have some difficulty, but suppose that we don't have any ties for X. And we have observations, suppose 1, 2, 3, 4, yeah, maybe closer one. And like this. We have how many points? 9 points. Then just we prepare as many knot points as possible. So the knot point 1 is here, C1, and just in between any 2 observations, C2 and C3 and C4, C5 and C6 and C7 and C8. So just 9 observations, so 8 knot points. Okay. Then we have very flexible curve. We have very flexible curve. So maybe fitted line is just a totally, fit this curve like this. C7, yeah, C7 and C8, yeah, so totally. But instead of allowing as many knot points as possible, we also penalize the G double prime of T. So G is the fitted curve. So we penalize the, too much, variation in G. So if G is very complicated curve, we penalize it. So the G double prime is basically represents curvature. So if curvature is very large, then we penalize it. So you can see, for example, here it's pretty ad hoc to fit the data because the curvature is pretty large. So we penalize it so that the actual fitted curve becomes smoother. So even if the piecewise estimation is allowed, maybe this kind of curve will be the final fitted line. So that is the smoothing spline. Yeah, smoothing spline. So we allow many knot points, but we penalize the size of the fluctuation. So if the curve is not very smooth, then we penalize it. And lambda is similar to the one in rich regression or lasso. So we have to optimize it in some way, but for now, lambda is just a constant. If lambda is large, then fitted line is smooth. Smoother GX. I would say maybe the GX, the closer to the constant or the straight line. So it's simpler curve. Maybe simpler, maybe smoother or simpler. G. And a smaller lambda, more complicated, G of X is estimated. So this one is, fantastic in the sense that we don't have to choose the knot points. so probably it's much easier to use. And we have the concept of effective degrees of freedom. So, this one have many parameters, right? So if we have 9 observations, then how many parameters? We have at first 4 parameters here, and when we across each the knot point, we have 1 additional parameters. So we have 8 parameters plus 4, so 12 parameters for 9 data points. But since we have penalty term, so this is effectively smoother curve. If lambda is large, this line is almost straight line. So effectively, we have less number of parameters. So we only have the small adjustment to the straight line. So if lambda is large, maybe effective number of parameters is 2, I would say. So how to define that effective number of degrees of freedom? So that is here. And the effective number of degrees of freedom is defined as here. So usually the df, the number of parameters, is a measure of model complexity, but the measure of flexibility for smoothing spline is lambda. So what is the relationship between lambda and the df? Then we define this way. So g hat of lambda is this one, and this is okay. So this is the fitted value for y1 to yn, but each of them are linear combination of y1 to yn. So remember that the linear regression formula. So beta hat is equal to x prime x inverse x prime y. So that means the fitted value y hat is equal to x beta hat. So that is the x times x transpose x inverse x transpose y. So this is the the sum matrix, and y is just the y1 to yn. So that means that each component of y hat is the linear combination of y1 to yn. Each component is a linear combination of y1 to yn. Yeah, and we define the effective degrees of freedom as, okay, so sorry, before that, we at first represent y1 hat to yn hat as just a linear combination of y. So y times some matrix S sub lambda, and this depends on the value of lambda. So I say the S sub lambda, and S sub lambda is n by n coefficient matrix based on x values calculated from x values. Maybe I will say x1 to xn. Then we define effective degrees of freedom as sum of diagonal term of S lambda. So df lambda is equal to just the sum of diagonal terms. Why sum of diagonal terms? Because that represents the how complicated the line is, because the maybe two most extreme case. So one is the simplest model, and two is maybe most overfit model or most complicated model. And the simplest case is the y1 hat is equal to y bar, y2 hat is equal to y bar, and yn hat is y bar. So everything is just average of y. So this is the simplest model. This is just the model with intercept. Okay. So in this case, basically the y1 hat is affected, the y1 hat is just the 1/n times summation of yi, right? So the y1 affects y1 hat only with the coefficient of 1/n. We have n observations, so of course the value of y1 matters more for y1 hat, but here only just 1/n times y1. So this is the simplest case, and the each of yi have, so each of yi hat has yi as the the right hand side, but the coefficient is always 1/n. And this is the simplest model. And the most overfit model is y1 hat is equal to y1, and y2 hat is equal to y2, and yn hat is equal to yn. Okay. So in such a case, basically the coefficient of yi on yi hat is equal to 1. So this df lambda is, for simplest case, 1/n plus 1/n plus up to 1/n. So this is 1. And the most complicated case, this is, okay, so 1 plus 1 plus 1, so n. So at least it sounds reasonable, criterion. So every other models have the df between y and n. Maybe it's possible that the df lambda is less than 1. So for example, we exclude y1 as the response to y1 hat, but that is pretty unnatural. So usually the df lambda is between y and n. Yeah, so if we use too much information of yi itself to determine yi hat, then the fitted curve is ad hoc and the degrees of freedom is large. On the other hand, y hat is y bar, then we literally fit the model y is equal to beta naught, so beta f, the df should be 1. So in fact, effective degrees of freedom is 1, since all elements of S lambda is equal to 1/n. Yeah, so maybe just in case. So first one, so the simplest case, S lambda is equal to just the every yi hat is the y bar, so that is 1/n, 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 so 1/n, 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 1/n. So the the diagonal term is just summation is 1. And the second one, the most complicated overfit model, the coefficient is just the 1, 1, 1, diagonal term 1, then 0, 0. So the summation is n. So df is lambda is 1, and the df lambda is n. Yeah. And how to optimize lambda? The lambda is determined by cross-validation. And for linear model, actually the leave one out cross-validation is ideal. And actually we can quickly calculate it. And okay, so this one, right? So this is the cross-validated error. But actually the cross-validated error is calculated easily. So here, g hat sub lambda superscript -I, this is the estimate when i's observation is excluded. I's observation is excluded from the model. So we are doing leave one out cross validation. So we exclude i's observation in estimation, then we evaluate the error size for i's observation. And that means that we have to fit the model n times. We have sample size of 100, we have to fit the model 100 times. But actually, this can be calculated in this way. yi minus g lambda hat xi. So this is just the usual fit. So using all observations. So estimate G hat lambda based on all observations. So we fit the model only once, and we calculate the S lambda. Maybe it takes some, small amount of time, but then take summation. So we only have to estimate the model once. So it's pretty easy. I mean, it's pretty quick, at least in a computer. So this is the way to fit the model. Yep. And this is the fitted curve here. So in this case, we have not. The age is, we have ties in age. So age is reported as integer. So we have not points between all, pair of ages. So here, the age 18 to age 80. So that means the not points are 18.5, 19.5, 20.5, up to 79.5. So these are not points. Then we fit the model, and then we do smoothing spline. Then we get this red curve or blue curve. Blue curve is actually the optimal one, and the effective degrees of freedom is 6.8. So it's about similar to the 6.8, so 6-degree polynomial. Six-degree polynomial, basically we have the degrees of freedom is equal to 7, right? Including intercept, we have 7. So the 6.8 is chosen. So that is complexity is about the same as the 6-degree polynomial. Red one, I don't know. So if we choose smaller lambda, then more complicated model will be chosen. Yeah. So maybe that we stop the materials here. Do you have any questions? Okay, so then we decide the presentation date. So we have the several presentation dates, so that's why we have to decide the schedule. So for April 19th and the 21st and the 28th, so we have 3 days. So 28th is during the final presentation, final exam period. So these first 2 dates are just usual class time. And since we have 15 students, we have to extend the time. I think that I explained it in the first lecture. So the last day, 5:30 to 8 p.m. Okay, so that means the maybe first day 4 presentations, each presentation 30 minutes. So maybe 4 people here and 5 people here and 6 people here. And you are supposed to submit the final project plan in late March. And after that, I try to respond your final project plan so that you are on the right track. And I prioritize to grade those for the early presentation dates. So if you choose early presentation dates, then you will get comments earlier. Yeah. So of course the later date has some advantages. You will learn more new materials in later weeks, but also the earlier presentation dates, you will get earlier comments earlier, and before final presentation period, you can do presentation. So we have advantages and disadvantages. And I haven't received any requests except for Mirror from Mirror. Mirror cannot make a presentation on 19th, but except for that, I don't have any. So any other? Oh, sorry. Sorry. I think I have to share screen. Yeah. Yeah. So now that we want to decide the presentation dates, and at first I want to see the list of students. Yeah. Okay, so anyone has any preference on the presentation date, at least? Like you are not available on some certain date?
I would prefer the 21st if I could, because I have 2 other exams on the 28th.
Oh, okay.
Are these flexible at all? Because I have another class and I don't know when the final exam is out.
Another class, yeah. Maybe
I-
Antarang, you have taken 50-30, right?
Yeah,
Yeah, maybe you can go on the first date. At least you
Sure.
know how presentation works.
sure, that's fine.
And maybe some other, at first, any students who have some time conflict with something?
Professor, can I have on 19th?
Sorry, Priyanka? Okay.
Yeah.
Yeah, I appreciate it here.
Me too.
Oh, Paula? Okay. And maybe if, 5 presentation in the first day is possible, maybe time pushes a little more, but any other?
Can I go on the 21st?
So sorry, the Sai? You're
Yeah.
Sai, right?
Mhm.
And 21st, right? So
Yes.
I already, Sai, sorry, Sarah and Sai, sorry. I was confused. Yeah. Okay. Yeah. Any
Yeah,
others?
Me for the 21st.
Marianne?
Yeah.
Any other preferences?
I'll take
Especially
the-
like undergraduate students for registering 18 credits. Maybe you can answer first. No.
If the 21st is still available, I'll,
Oh, Brennan?
yeah. That'll give me a week for my master's presentation.
Oh, yeah. Your case, I think April 19th is a little tight. You're right. Or maybe 28th. Do you prefer 21st, 28th?
As the 28th, that's during final exams.
The final exam period, yes.
I'll stick
Which
with
is
the
better?
21st because I don't know what my other final exam is either.
Okay, okay. Any others? The Nick or Rajesh or
If the 28th is cool, I'm cool with the 28th.
sorry, which date?
The 28th.
28th, yeah, sure. Rajesh?
Yeah, I can do the 28th as well.
Okay. So all of you answered, maybe only 9 students here. So maybe, okay, so I think it's pretty good. So we have 1 slot in the first day, on the first day, and 1 slot 21st, and 3 slots. And okay, so that's great. Okay, so I will send the schedule after the lecture, so I just confirm it. So it's on screen. So just make sure that everyone is fine with this. Antarang and Priyanka, Paula, Sarah, Sai, Mariam, Brennan, Nick, and Rajesh. Okay, great. Okay, so
Is class only extended on the 28th then? For the
yes, that's
presentation?
true. Yeah, 19th and the 21st, I just want to keep it, and the 28th, yeah, but if 5 presentations, maybe we may extend like 5 minutes, 10 minutes, but not much. Yeah.
Okay.
Okay, so that's great. Okay, so now maybe we go back to the lecture.
Professor, I have one question before we go back.
Yeah, sure, sure.
So instead of posting our presentation on YouTube like we did on with Stat 5030, we will have to do it in class here, right?
Yes, in class. Yes, you're right. You're right. So sorry. Yeah. So yeah. So yes. So you have to be in class. So 19th. That means you have to share screen on 19th. Then make a 30 minutes presentation. Yep.
Okay. All right. Thank you.
Yep. Okay. So
I had a question because I have a time conflict with 428.
Sorry,
do we-
the first
oh,
speaking, sorry.
Paula.
Paula, yeah.
Yes, I was just wondering, do we have to attend all of the other presentations too?
Yes, but yes, that's true. But if you have some severe time conflict, such as you have three exams in 24 hours, then you can send me the reason that you cannot take it.
Okay, thank you.
Yeah. So basically, you will get some small credits to attend each lecture. So I will ask you to comment on each presentation, and that will count towards quiz score. So yeah, but if you have some specific reasons, then I will just adjust it. So yeah. Oh, sorry. Yeah, so attend all presentations, but if you have some time conflict, that's fine. And yeah, especially the final exam week, you have 3 exams in 24 hours, then that's fine. You can send me your exam schedule.